All right. So, for those of you who don't know, I'm Christina. I am taking the next 28 days to revamp some of my knowledge in deep learning, GPUs, um, linear algebra. Uh, 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 there's one more that I forgot. And I'm streaming so that I can hold myself accountable to be present and online every day at 6 to get through these notebooks. We're almost done with the PyTorch refresh, and we'll be going into C++ from Monday. We've gone through an introduction to like PyTorch, going through their initial basic documents um, on the pytorch.org website. Now I'm going through the Practical Deep Learning for Coders book by Fast AI, and we'll be going into kind of half their API, half um, PyTorch, and like how their API can speed up your PyTorch implementation, since PyTorch is a little bit slow, which is fine. And so today we're going to be looking into their NLP document. Is chapter 10 of their book. You can find it on GitHub, in the Fast AI GitHub repo. You can also find it at their website, courses.fastai.org. It's been around, let's say, almost 5 years, or almost exactly 5 years. So it's a really well-known group that provides these tutorials by people who've been in this space a long time. So yeah, we're going to get into NLP for deep learning, not just regular NLP that I grew up on back when it was just text mining a document and pulling out the frequencies yourself when there's like back when Python 2 was a thing. And what has it come now? So technology moves so quickly. All right. So we're going to go through this book. It's probably going to take us an hour to an hour and a half to get through this book. If we have more time, I will go to chapter 12 or 11. I might skip 11, do 11 tomorrow, but we'll see. So we're going to look at how NLP, the pre-trained model, and basically transfer learning. Transfer learning has only become popularized in the past 3 years, I'd say popularized, maybe research definitely longer than that, but it was a thing back then, but a lot of people aren't using it, and now more and more people are being used it as a lot of these pre-trained models became available in the hyperscalers. By hyperscalers, I mean like AWS, GCP, Azure, and there's a bunch of other people now with different pre-trained models so that you don't have to do everything. So, and that's called transfer learning, which is a whole field that we'll get into, and you can use it for both NLP and computer vision problems. A language model is a model that is trained to guess what the next word in a text is based on the words that came before. And basically, it's looking at the patterns in the text, the phrases, the sentences, what it appears next to kind of determine that. And this is a kind of self-supervised learning. You don't need to give labels to it. You don't really label NLP model all the time in some scenarios, especially not this one. We just feed it lots of text. Now, it can be labeled. I'm not saying it can't be labeled. I've worked on labeled NLP, but that is a way to help tune a model, especially if you're looking for. We'll get to that. I'm getting ahead of myself, going down rabbit holes. But let's start out with how it basically, if it's self-supervised, what we're talking about here, it automatically gets the label from that data. And it guesses the next word in the sentence, and it has an understanding of whatever language that model is built in. So it can have an understanding of English, of Spanish, of Arabic. There's specific pre-trained models for each one of these languages, because languages are different. And not all NLP is advanced in every language either. It just depends on how many researchers they have working on it. And I can't wait till we get more and more people with these language skills building out these models. So they are going to be using and looking at, I guess, this IMDb reviews that was pre-trained on Wikipedia. And yeah, even English is not English, right? There's UK English or British English, American English, Indian English, Singaporean English, but also how we choose to write, such as how you choose to write on Wikipedia English versus how you choose to write on IMDb English or Twitter English, right? How and people communicate across different platforms, meaning varies how the output of the data is. And so we might need to fine tune the pre-trained model to get it to match what we're looking for in that new data set, right? Even if it kind of knows the basics, giving it more information will help it. And that's kind of the same principles of how you would fine tune in a large language model. So it helps it get used to the style of corpus that we're targeting. So there, one reason why we would want to fine tune the language model before we fine tune the classification that we're looking for is they give this example. So for the IMDb sentiment analysis task, the data set includes 50,000 additional movie reviews that do not have any positive or negative labels attached. Since there are 25,000 labeled reviews in the training set and 25,000 in the validation set, it makes it 100,000 movie reviews altogether. We can use all of these reviews to fine tune the pre-trained language model, which was trained only on Wikipedia articles. This will result in a language model that is particularly good at predicting the next word of a movie review. This is known as the Universal Language Model Fine Tuning, or ULM FIT approach. And there's a whole paper on it. I've read it before years ago, probably when I was taking this class, but it's here. And it shows the extra stage of fine-tuning the language model prior to transferring learning, and then to the creation, the classification task, resulted in significantly better predictions because it's a fine-tuned closer to what you're actually the data you're looking at. So Wikipedia pre-trained model, IMDb language, fine-tuning, then you classify into the positive or negative reviews, right? So how do we pre-process, right? Sentences, documents, phrases, they're all different lengths, and we can predict the next word, obviously, with a neural network. We used to use just getting random forest. We had a whole thing on that. But we can use a neural network too, which makes it a deep learning problem. Now, if we make a list of all possible levels of the categorical variable, replace each level with its index in that vocabulary, create an embedding matrix for this containing a row for each level, use the embedding matrix as the first layer of the neural net, that is how we're going to train the neural net for a single categorical variable, right? Not a multi-classification. You can start out with, obviously, if you have a ton of documents, concatenating those documents into a long string, splitting on the words, and giving us the very long list of words or tokens. And our independent variable will be the sequence of words starting with the first word in our long list, ending in the last one. And the dependent variable will be the sequence of words starting with the second word and ending in the last word, because it'll be predicting the next word. That's the dependent variable. Our vocab is a mix of common words that are already in the vocabulary of our pre-trained model and the new specific words, which is the corpus, which is IMDb. And our embedding matrix will be built accordingly. So, common jargon and steps. Tokenization, meaning you're pulling out each word, right? I hate jargon. Numericalization, making a list of all the unique words that appear and converting that word into a number so that you can look it up by the index of the vocabulary, right? large language model data loader creation. In this case, FastAI provides this for us. And then the creation of the language model, which we will be using a recurrent neural network to make this happen. And when we get to the other chapter, we'll get deeper into that as a review. So there are many ways to tokenize words. I think they are going to just have it split word tokenization. So you can just import a word tokenization from Spacey or NLTK. You don't have to split on the word yourself. That's how you used to have to do it. Now it's built in. And so we're going to load and import our data. We're going to get the files and, get the train test and unsupervised that I'm guessing. And because it's not a validation set, unless they just rename it something else. And we'll open it, and that's kind of when it gets the first 25 characters or words. Yeah, tokens. No, characters. Characters. So when using Spacey, and there are differences between using Spacey and NLTK, which I don't remember off the top of my head, but I might actually look up because I actually have not had to think about this question in years. I've not had to think about it. Okay, Spacey is object-oriented, and string processing is what NLTK is. Anything else? NLTK is more comprehensive, according to these guys. Slower results, that typically comes with comprehension, but that doesn't, mean anything. Spacey, more useful in development and production environments. Are we sure? Faster for sure. So it really just, I guess, depends. Their algorithms are slightly different too. So we'll get the word tokenized out. And then they have this method to display the results. And it displays the first n items in a collection along with the full size. So first n items in full size is what L uses by default. Note FastAI tokenizers of a collection of documents tokenized so we can wrap the text in that list. Okay. So they import word tokenizer. They tokenize this text that they imported, right? So they imported where? Read the text. Here. This is that text. They open it. They read the first few lines. And they split it off into independent tokens. And they print the first 1, 2, 3, 4, 5, 6, 7, 8, 30. Yeah, tokens. And a token, if you notice in here, this is a token in and of itself. So you will have that there. So you might have to remove punctuation depending on what you're working on as a problem. So it separated out all the words and the punctuation. Okay. Share screen. Thank you for letting me know. There we go. See, I forget something every time, either my audio or to share my screen. So I hope you pulled up the notebook. And definitely let me know next time. I don't think it's actually showing me the comments from every location I'm streaming on. I would guess I need someone to actually stream with me just in case my stream software is missing a comment, because I don't know. Okay. So then we can add some more functionality, right, to process these. And these special tokens, these ones starting with XX, it indicates the start of a new text. So this was the beginning of the line that we had, beginning of stream, and it recognizes the start of the larger document, I guess. And it will forget what was said previously and focus on the upcoming words. So it's specifically for the Fast AI API, and they apply their own rules to it. So the rules replace a sequence of 4 exclamation points with a special repeated character token followed by the number 4. So I guess you have to check their API to know all of the special characters that it will use to indicate sometimes. And it will also replace capitalized words with a capitalization token and then use the lowercase version so we don't have to. It can recognize the word whether it's capitalized or lowercase. So indicates this one and is an indicator that the word next to it begins with a capital and everything else is lowercase. So if we go back up here, this means the next one is capital. So this is supposed to be a capital I, and this is supposed to be a capital T. And then this indicates the word is unknown. Um, and these are the default rules. As always, you can look up the source code, and figure out what it all means. But they have it here. So here, if they were to take the tokens here, say beginning of the screen, they print the character. It was supposed to be capitalized. They put it. This is a space. Replaces a character repeated 3 or more. And so repeated character, repeated this many times, and what was the character? And then it says up, replace all caps. So this was capped, and now it's lowercase. Nifty. Very nifty. So what this does effectively, instead of you just lowercasing everything or transposing all of at least these unique ones yourself, it gives you a framework for doing that with their API so that you don't have to do that pre-processing step. So in addition to the word tokenization approach seen in the last section, there's subword tokenization, which this is a Chinese sentence and an English sentence. And Chinese does not space. In fact, they don't have a they don't have a concept really of a word. It's constructed language. And we're not a constructive language. It's very different. So if this is the situation, what can you do? So if you analyze those documents and find the most commonly occurring groups of letters, these become a vocabulary. And then you tokenize, you can create your own unique vocabulary. I've done that with like pharmaceutical data and the names of, just information that's unique to those data sets. So in this case, to give us an example, they're going to just pull 2,000 movies and reviews, not movies themselves, but reviews. They're going to tokenize it, and pass it a list of words, right? And they're going to create the subword tokenizer. They're going to use setup, which is their built-in method, and that automatically Oh, so if you use their pre-processing stuff, you don't have to pull it yourself, but they're trying to explain it to us, so it's pulling it yourself. And so this now creates a subword of this string, and it adds a underscore to it. And if you want to have fewer characters or, separate ones, they will do that. And if you have a larger one, it'll do it like this. Um, the subword vocabulary size depends on your requirements, but you can scale up or scale down. It can handle genomic sequences, which is interesting. Music notations, MIDI, yeah, that's kind of cool. And it's becoming more popular to do it that way. So now, when we numericalization and we're mapping tokens to integers, right? Uh, and the steps are, identical to what you do for the category. Just call after you tokenize it, you can call setup on numericalize. Yeah, so that's here. They're just pulling a small subset to work on. Okay, so they instantiate the instance of numericalize, and then they set it up, and so they do it for 20. And you will have their special rules tokens appeared first. So this kind of organizes it. Every word that appears once in frequency order. Uh, and then with the most common, then with special characters. So that way you don't have a large embedding matrix. Makes sense. They do have a minimum frequency that you can add to it to get the minimum times a word needs to appear for it to be added to the vocabulary. Oh, the days you had to do that by hand. So these are now the integers for the tensor. And this is what it equates to. And these would be repeated. And what is it repeating? Okay. So now they're going to show you how to batch it. So again, in deep learning, our tensors have to be of the same size. And so in order to that, we need to resize it. And if we tokenize it and get the special rules, it changes our size to actually larger than the original. So instead of having however many tokens this was originally, you now have 90, right? And if our batch size is 6, like we're training 6 tokens at a time, we need to break this text into 6 parts of lengths of 15. 15 times 6, I'm assuming, is 90. Yes, I'm American. I can't do math in my head. I don't have a calculator in front of me. So let's say you input this stream, and we get the sequence length and the batch size. We create an array of the tokens, and then we just add it to that, and we display it as HTML. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There we go. And 1, 2, 3, 4, 5, 6. And it displayed that for you. Batches, sequences, columns and rows. Now, we can't, Scalability, always a problem, like how much server time, computation time you need to use varies. So um, how do we add it to the model is the next question. You would, yeah, like I said, create this. And you feed that array, and then you feed this array, and then that array. So the first step transforms the individual text into a stream. Yeah, you randomize and shuffle each entry to the new stream. Then you cut this stream into a certain number of batches, and they would shuffle their collection of documents and concatenate the streams of tokens. One second. So their data loader. This time they're just going to use their data loader. They load their data. They confirm the expected results. They join it together. And they have the string. And you can handle the tokenization and normalization with a text block is passed to the data block that you constructed with the information. And then it can be passed to the tokenizer and the numericalizer, which is all fast API built-ins. Convenient. So they get their sets, they split it up, they load it into the data block. Sorry, family. I ignore all other text, but family, I don't. Okay, we need to tell the text block how to access the text. And that's what this folder does, okay? So let's talk about fine tuning. To convert the integer word indexes into activations, because that's, we have to have activation layer for the neural network. We can use the embeddings that they did previously, that we've been doing the past week. Then we will feed those embeddings to a RNN and use the architecture for a AWD LSTM, and we can merge it. So we create a language model learner, load our stuff, and have it print out the metrics, right? And this perplexity is new. So the perplexity metrics used here to often use NLP, it is the exponential loss. Okay, cross empathy. Why do we keep naming stuff different? The default is cross empathy loss. So we've done that before. Jargon gets you every time. We also include the accuracy metrics to see how many models in the right. So yeah, we've seen this diagram before. We only need one fit cycle to get one cycle out, and it'll freeze the model. We save it. We can load it again, unfreeze it, do it again. And then we can save the encoder, the final layer. Um, so actually, me being distracted. So to fine tune, we had the Wikipedia data initially. We now have the batch IMDb data that we pre-processed. And we're going to put it through the training to tune it out. All right, so next we need to classify the text because they're trying to predict the next word in line. So I guess before we do that, they're going to have us do a text generation model. I don't know why, but I'm guessing they're going to tell us. And so we're going to generate text, and this is the prompt. This is the words, this is the sentences. And we're going to be setting this stuff. So I like this movie because we give one sentence, it gives because, and then it gives two sentences of 40 words total, I guess, for this. And they do it again. And they do it again. I picked a random word based on the probabilities required by the model so we don't get exactly the same review twice. So it pulls a different one. It doesn't have any knowledge that was programmed into it around the structure of grammar. It just clearly learned English and formulated it out and knew how to capitalize it from just reading a ton of text, right? And we notice something off because of how we read it, right? So now classifying. So we need to load the data in the custom data. We need to get it from the folder, split the information as we need it, load it in the right size, and give it a sequence links to look at. And then we're going to batch it, right? So show you just this batch. 1, 2, 3. Okay. Right. So is LM is false is a default, and that's telling us that we have regular labeled data rather than the next tokens as labels. So it's just labeled data that we're adding in. Make sure we know what we're telling it. Yeah. And the challenge is collating multiple documents into a mini batch. So here we have our tokens that are samples. We load in data, it correlates the items and turns a batch into a simple tensor. And cropping, padding, squishing, make all the inputs the same size. Cropping might be a good idea for documents. Yeah, but say you can't actually squish like you would for an image. We expand the shortest texts to make them all the same size. To do this, we use a special padding token that be ignored by the model, but it just makes the text the same size. Batch them together, right? For this, right? So we load the data. We run a one cycle, And the last step is to train discriminative learning rates and gradual unfreezing. And since it's an NLP model, we find that unfreezing a few layers at a time makes a real difference. So, in just one epoch, we can get the same result. And if we pass negative to freeze all except two parameter groups, this is what happened. The last two parameter groups, so it pulls the last two. So we run it, pulls the last two, and the loss is down after it fits. And then we can unbit the last three, and it does better. If they unfreeze the whole model, this is what it does. So they reached a good accuracy score, but by training another model on all the text read backwards and averaging those predictions, you can actually get to 95.1, which is what they did in the ULMF paper. So it was beaten by training a much bigger model using expensive data augmentation techniques and translating those sentences into another language and back using another model for translation. So by adding translated information, that actually can get it higher. But using a pre-trained model, fine-tuning it helps us better. So they generate fake reviews or help classify them. And I'm sure there's a lot of people generating fake reviews now with this technique. Fraudulent accounts, yeah, fake reviews, posting. It's a lot. So in analyzing the reviews, he found they were fake. The same sort of Mad Lib style merge. Americans, as opposed to Washington bureaucrats, deserve to enjoy the services they desire. Individual citizens, as opposed to the Washington bureaucrats, should be able to select whichever services they desire. Less than 80,000 of the 22 million comments could be considered truly unique. That more than 99% of the truly unique comments were in favor of keeping net neutrality. Yeah, a lot more improvements. And this is a book written when ChatGPT 2 was a thing. And comments on unpopular opinion GPT-2. And imagine what happened if the bad actors decided to release. Yeah. And it is being released. I think people are doing fake stuff all the time at scale to make it look like they actually interacted with your content or know something. Auto-generated game network. Person does not exist. She just posts auto-generated content. Wow. Why would you do that? Okay. People. So this is just a quick middleware for them. And so we'll do this quick. Data munging, one of the most annoying things we have to do. So they talk about their tokenizer, the numericalizer. Actually, I'll probably skip that because, I mean, this is just about their API and the stuff that's available to them. You can read the docs. Let's go to the NLP deep dive so we can finish NLP today. To understand this, they're going to be walking through what a recurrent neural network is and why it is, I'm guessing, useful. So, load data, read lines, put data into different stuff, strip the length, split it open, get a list of unique tokens, enumerate that stuff, and that's kind of where we start. And now we have a small data set which we can do stuff on, right? So we're gonna predict a word based on the previous 3 words in the document. And basically, if they create a list of all 3 words, then it gives it kind of a set to look at to determine the options for the next word it's going to predict. Oh, I'm sorry. This happens every day. I always get tired when I get in the seat to do this stream. But I guess it is near my bedtime. So then it converts it to numerical values. So 1, 2, 0, 1, 2, 3. That's 1, so it repeats 1. 3, 1, repeats 1, 4. Because this is outside 4, but it's also 4 in here. So it makes sure it maps the dictionary. And it has what it needs to look for, right? In splitting everything up. So predicting the next word, it was this one in a set of 3. Then if you take a next set of 3. Oh, how does the split work? How does the split work? Let's first with the token, I just confirm what it looks like. Previous 3 words. Right. So a list of 3 words and then the next word. A list of 3 words, then the next word. A list of 3 words. Oh, so this is 3 words, next word, 3 words, next word. Because that was the next word. So then it's that word, 3 words, next word, then that word, 3 words, next word, that word, 3 words, next word. Okay. Ooh. Now we can do with tensors with turn those into actual numerical values, which is what they do here. And then we can batch using the data loader that we made. So we'll split the sequences randomly so that it is in and out of order, right? And you're going to batch it in 64s, right? And so input and return spatial, 3 standard linear layers, but with 2 tweaks. The first tweak is that the first layer will be used only for the first words embedding as activation. So the second layer will be used as second words embeddings plus the first letter's output activations and because it's recurrent. And the third layer will use the third words embedding plus the second letter's output activation because it's recurrent. The key effect is that every word is interpreted in the information context of any word preceding it. The second tweak is that each of the 3 layers will use the same weight metrics. The way that one impacts the activations from previous words should not change depending on the position of a word. In other words, activation values will change as the data moves through the layers, but the layer weights themselves will not change layer to layer. So as it moves, the data changes, but the weight of the layer doesn't. And it does not learn the sequence position. It just learns to handle all the position this way. They create one layer and use it multiple times. So going to use the language module. And that's this, right? And so it has embeddings, layers, it has the ReLUs, which I believe it converts zeros to continuous numbers or negatives to continuous numbers. I really do gotta remember that stuff. I feel like I can always reference that. And I would naturally pull up documentation and code next to it, is what I do 90% of the time. Um, input is hidden, input hidden, so and the layer to create activations for the next word, hidden to hidden, final layer to predict the fourth word, hidden to output. And that's what they mean here. And if you look at it, this is what it means. Inputs, ReLU, hidden batch activations, softmax, batch classes. Each shape represents an activation, and triangles for output, hidden input. Okay. So the arrow represents the actual layer computation. The linear layer followed by the activation function using this notation. So input to hidden, hidden to output, hidden to hidden. So these are in the middle. And word 2 input. So word 1 input, word 2 input, word 3 input, activations. That's how it forms it. And we just put it in the vocab list, batch sizes, the loss function. Actually, when I run it for one cycle 4 times, and it does that. And we need to check if it's any good. So we predict the most common token first. So the most common word was 1,000. And so they find it, and then for each one, they loop through some and get the vocab, right? So most common token was the one at index 29, which is the word 1,000. And it's 15%, which, look at the loss, is better than you think. All right, so now we've changed this part. And to do the recurrent network, we simply replace the duplicated code that calls layers with a for loop and simplify the code. Because we do the layers 1, 2, 3, 1, 2, 3, right? Right here. The power module is sequence of different lengths. Here, here. And then you run your loader again. And that looks the same to me. That's a little. Yeah, I don't think it's that good. So one thing that seems problematic is that we're initializing our hidden state to 0 for every new input sequence. And that's a problem because we made our sample sequences short so they could fit easily into the batches. But if we order the samples correctly, these sample sequences will be read in order by the model, exposing the model to longer stretches of the original sequence. So it's like too short to really predict well because there's no original order it was in. Why only predict on the fourth word when we could use the intermediate predictions to also predict the second and third words, which would give it more signals to understand how to predict the next word in a sequence, right? So to fix that, they move the initiation. So to fix the first one, which is they start the hidden state at 0 each time, they move the initialization state and hidden state to the init function. So this is now here. And if we go to this code here, it was here. So they move that. But by doing this, it affects my neural net as deep as the entire number of tokens in the document. So really long. It will make the layer a 10,000 layer neural network. Okay, so this is an unrolled representation. And that means to see why it will create all the layers, we need to consider the original pictorial representation of the neural network, right? Before refactoring with the for loop, we can see each layer corresponds with one token input when we talk about the representation of before refactoring. So if we go up to, not this one, this is refactor, there's a for loop, to this one for every single one. Yeah, it was doing it. So that's why we get that large, that depth in the recurrent derivative if we do it that way. So it'll be very slow. So in order to do that, we don't need to back propagate the derivatives throughout the entire implicit neural network. And so that's why we remove all gradient history and we detach it. So this is why we now add detach so that it doesn't make all of those layers. And that gives the new version is now stateful because it has to recognize and remembers the activations between calls instead of deleting them out and going from there. And so it'll have the same activations, whatever sequence we pick, because the hidden state will remember the last activation from the previous batch. The difference the gradients computed at each step. They will only be calculated on a sequence linked tokens in the past instead of the whole stream. This approach is called backpropagation through time. And that's basically treating a neural network with effectively one layer per time set as one big model and calculating the gradients in the usual way to avoid running out of memory. So to use it, we want the samples to be seen in order so it views everything as one kind of in ordered stream and have more information that way. And if the first line of our first batch is set to 0, then the second batch is 1, well, in position, right? We're doing this, okay. And the last one is to do this, we're going to rearrange our data. First, we divide the samples into the length divided by the batch set. 64 equally sized pieces, right? No remainders. So that's what we get. And a chunk of continuous text of 3 times m, which is each text is a size of 3 in each line in that batch. And this is the chunking code here. And drop the last batch that doesn't have this shape. So anything that's left over that doesn't fit the even shape, it just gets rid of. And we can also read it in order. And it'll treat training loop via the callback. Okay, so next chapter we'll talk about callbacks. We get more into stochastic gradients. And actually, I don't think we'll do that chapter. Where is it? Because we only have time for convolutions and maybe ResNet before we change what we're looking at for the week. Okay, my bad. Go back. Scroll down. That's too far down. over here. Yeah, we can implement methods original state, and I'll make sure that we start with the clean state before we end the continuous touch check to move that. So now they're going to run the learner with the new code, size 64 crossing the accuracy model resetter. And now finally we get a better learning loss on the training set, and technically on the validation set, and the accuracy has improved. So now that we solved giving it more data to look at in order, we're going to solve giving it more signal, right? So predicting every next word, not just the second word in the sequence if you give the first one, but give the third one, the fourth one, the fifth one, the sixth one, and so on. And so to do that, we have to feed it the updated weights, right? So initiate with zeros, input word, and repeat for all of them. Don't have specific ones that we pull out anymore. So the dependent variable now has each of the next 3 words instead of 3 sequence length. So I plus sequence length here, I plus sequence, so it iterates through that to make sure it's looking at the next one. So 0, 1, 2, 3, 0, 1, 2, 3, 5. Then it starts with this one. So it does this one, the next one, the dependent is this one. Okay, so if we look here, same, this is changed. It returns the output shape of BS times the sequence length times the vocabulary size. Since we stacked on that dimension and our targets are shape, batch size, sequence length. So we need to flatten those before you can use them with crossing MP. Okay. We get the loss function after we do that. And then you can use it. It does improve, but it gets worse on the validation set. Okay. This is more complex. They add more training, but the results vary wildly. Because look at that. It's everywhere. So the gradients are either very small or very large. So let's go deeper into more layers. So now we create a multi-layer neural network. A multi-layer recurrent neural network, to be exact. And so one that does the initial one and takes that and repeats it. Unroll representation looks like so. Input word 1. Send that to input word 2. Then that there to the output. Input this one. Hit the next one. Keep doing that. So Now this changes. All right. So it doesn't it initialize a whole layer of zeros. It looks like. And then runs it for cross sympathy. It also takes the hidden and the vocab size. And then it removes this and it just adds that recurrent network and the input to the hidden, and then the hidden self, which is this one, detaches from it so it doesn't just make a ton more layers that way. And then goes to here. And then it resets itself. Okay. So then we can run that. Yeah, that is very disappointing. So when you made it bigger, it exploded or vanished in your activations. Yeah, I was wondering about that. I just felt like it was a bad idea. Why would you do it that? I guess they were making a point. Sometimes a chair can be a little. Okay. Yeah. Yeah. Okay, so if they call detached list and they have more layers and how this needs to be trained is going to vary by whatever you're working on. And that's just going to multiply your tensors or your layers or whatever, depending on how you make it happen. And you just have to keep doing more matrix math. So what are you actually going to do? LSTM. So in order to do that, we can add different layers. LSTM, yeah, gated recurrent units, and you can add this layer, one of these layers in. So if we do LSTMs, yeah, it is old. So needs to remember the names of the people. And since RNNs can't retain memory, what happened early in a sentence, which is the motivation for another hidden state, and that's why we use LSTM, keeping a long short-term memory. Yeah, it is, huh? Okay, so building it from scratch. I am not about to look at building this from scratch. I don't think you need to know. But if you were to do the math, this is the structure. I don't even remember. Oh, they have it for you here. Trigonometry. And I did not get along. Oh, the agony. So I think let's not look at that. I don't need trauma on a Saturday. Okay, so what do we do need? Okay, so the first gate, looking from left to right, is called the forget gate. Since the linear layer followed by a sigmoid is output, that's consistent. It puts it on a scale of 0 to 1. We multiply these results. Cell state to determine what information to keep. Second gate is input gate. And it works with the third gate, which really doesn't have a name sometimes. It's called the cell gate. Is just to update it, right? And if you need a gender pronoun, we can need to replace information by the general pronoun to forget it, right? Then you have the output gate. So what does that look like now? We create these gates with a linear and NI, NH. Let's look at what it is. So if those N_1, IN, and hidden, so input, hidden, and add those together. Oh, trigonometry. Okay. And you refactor the code. This would be the original. I'm not going to look at the original. I would rather look at the refactor. So if we optimize it, we just need input to hidden, hidden to hidden, and what those calculations are. We set the state, and then one big multiplication of those matrices of the input, the hidden layer, and then you can set your gates, and those gates are mapped to sigmoid, and then you have your cell gate, and you gauge your render tangent on it. You just see in your H, and then you return it. And all of this really is math. And so, honestly, it really is just math. Trigonometry, but it's just the math. You would need to understand. You don't need to understand the principle to code the math necessarily. I've seen people not understand the principle to code the math, but you just take this and use it. Now, that's with the math by hand from scratch. This is, again, it all rolled up for you, which is so much better to look at. I don't feel triggered at all. I like calculus without the trigonometry. But there we go. And then it also changes to run the loop for the list comprehension for the detached layer. The detached layer is not attaching, but detaching it and not remembering the information. And then it also changes this one so that it works in the range. Then we can run it and we can see what this does. This does actually get better. Yeah. And this is definitely too accurate. And so regularization right. It's hard to augment text data to improve this. So we're going to look at dropout, activation regularization, and temporal activation regularization. Could allow LSTM to beat the state of the art. So that's where we get the name all-wheel drive LSTM. Got it. So LSTM with these is all-wheel drive LSTM. So it just drops out stuff, right? So dropout is a regularization technique that was introduced in that paper. And the basic idea is that randomly change some activations to 0 at training time in a random subset to make sure all the neurons are actively work toward the output. It's like a random dropout of information. So if you were to just use the zeros without anything else, you would have a problem training, right? Because they'd be on different scales. So you rescale the activations. And you just average the zeros, at least 1 minus p. And so this is a dropout layer here. If not training, return. Create a mask and Bernoulli method. It's creating a tensor of random zeros. Okay, turning the random zeros with a certain probability and the ones with a certain probability. So it just whatever probability it chooses. Then it's multiplied before dividing by that probability. Which is available until if we're doing training or inference. So if it's not training, you need to do this. If it's inferring, drop out before passing the output of the final layer will help reduce overfitting. Right. So it okay. So dropout for training and validation are two different things. So activation regularization and temporal activation regularization are varied by weight decay. When applying weight decay, we add a small penalty to the loss that aims to make the weights as small as possible. So the final act for, if it's activation regularization, the final activation reduced by the LSTM, that we will try to make as small as possible instead of the weights. To regularize the final activations, we have to store those somewhere, then add the means of the squares to them to the loss. So loss plus the multiplier and the activation squared, take the mean. In the temporal regularization, if they were read in oral, so temporal time, adding a penalty loss, we're making the difference between two consecutive activations as small as possible, so the ordering. The sequence length, the batch size, and the hidden layer, multiply those together, and read the consecutive activations. You do the same thing. So activated are two hyperparameters returned to make this work. We need a model to drop out, return things to proper output, the activations pre-dropout and the activations post-dropout. And the activation regularization often applied to the dropout activations, while this is the temporal ones are non-dropout activations. So the ones that you dropped out, you do this. The ones you don't drop out, you do that. And then you callback that will apply. So if we use this callback, it does it for us. See, I like it when people spend time to make my job easier, but you have to understand how to use it. So if we combine them, right, wait time thing. The input embeddings represent mapping from English words to activations, and the output layer represents the mapping from activations to English word. We might expect intuitively that these mappings could be the same. We can represent this in PyTorch by assigning the same weight matrix to each layer. So we now have the embedding. We create the LSTM. We get the dropout layers. We run the linear. We get the weights. We do the batch zero. That's just the model. Then we forfeit the neural network. We get the dropout output. We attach it so it does remember. And then we reset everything. And we regularize everything when we do the learning. So if you switch to a text learner, it knows it needs to regularize, and so it's there anyway. So you don't have to think about it. So they run it again, and now the validation set is better. The training set is probably still a bit overfit, but it's better. And so that is the end. And these are more places to use dropouts. Cool. I feel like I need to read this lesson again. Because I am not new to deep learning for NLP, but I've never actually done it on a job, you know? And I think I learned stuff once I do it on a job or in a data set. And I haven't had to do a portfolio in so many years. It's hard to do it and do a job. So it's 7:15. What I think we'll do is save this for tomorrow. And yeah, we'll save the next one for tomorrow. Oh, actually, did I skip? I feel like I skipped. I meant to do 12 and I just read through 13. But, Oh no, we did it. Okay, so tomorrow we'll do 14. Um, look at resonance and arc details. We might actually have time for accelerated stochastic descent. All right, well, if you have questions, DM me. Thanks for tuning in and holding me accountable to study. And I hope you learned something too. And we're able to set aside time to learn something new. We have one more day of PyTorch studying, and we will start some CUDA programming. I could do PyCUDA. I kind of really don't want to, but I might go ahead and do it because relearning C++ will be incredibly hard, I think. Maybe not, though. I mean, I've had to use it at work. I've only used it in an academic setting. So, okay. I will see you guys tomorrow.